held up at a height and it's going to drop towards the ground. Nothing really creative. It's going to get faster and faster as it hits the ground. So we know that it's gaining velocity. And since velocity means we're moving, that means we've got kinetic energy. We want to read this carefully, and we see that the system consists of only the box. So when we have a system of just one thing, that means that we can only have kinetic energy. So the Earth is going to do work on the box. And when we do work on something, we change its energy. In this case, we're going from no kinetic energy to some kinetic energy. So the way we represent that through our bar chart is we show that there's nothing at the point of release. And then once it's at ground level, it has gained this kinetic energy. The force of gravity did work on the box to increase its kinetic energy. Let's get a little more towards our topic for today, which is conservation of energy. You've probably heard that energy can be neither created nor destroyed. It just transfers between different types. We want to see how we can represent that in a similar way that we just did with our energy bar charts. And we're going to be able to show what types are present at different points throughout a particular scenario. Here's another example, but it's going to look pretty familiar from what we just saw. It's still our box. We're going to drop it. It's going to fall. It's going to get faster and faster. But if we read carefully, we see that there's a little something different in the problem. It says that we're looking at the system of the box and the Earth, the box-Earth system. So now the Earth is a part of our system. So that means we can have gravitational potential energy. It's raised up a height. And if you remember, gravitational potential energy is mgh. And so we've got our h right there. So at the beginning, it has height. So that means we have gravitational potential energy. And at the end, we already said it's going to get faster and faster and faster. So that gravitational potential energy transforms into kinetic energy. And so if we have conservation of energy, we should have the same amount of gravitational potential energy at the beginning as we do kinetic energy at the end. So we want to represent that in our bar chart. And that's what it would look like. So notice we had 4 units of gravitational potential energy and 4 units of kinetic energy, showing that we had conservation of energy. The energy before equals the energy after. This assumes that we have no non-conservative forces. We don't have air resistance. We don't have friction, so we can have the conservation of energy. So let's do a little bit of practice, maybe with a little bit of a different type of situation that shows another type of energy. So here's a box. It is going to compress a spring. When we compress the spring and then release the box, it is going to travel up a ramp and be launched like a projectile back from unit 1. So we want to see what type of energy is present at each point, the beginning and at the end here, where we've located that the box is actually at its highest point and it's still moving. So take a minute and think what types of energy are present at the beginning and what types of energy are present at the end. Then we want to look at our bar chart. So hopefully you said that since there's a spring present, we use spring potential energy. And then at the end, we have height and we're moving. And so that means we've got kinetic energy and we've got gravitational potential energy. So remember, we've got conservation of energy. That ramp is frictionless, so no non-conservative forces. So the amount of energy before has to equal the amount of energy after. So what could that look like? There's our spring potential energy to begin with. Notice that it's 4 units. Then we've got kinetic and gravitational potential energy at the end. Each of those is 2 units because we have to have the same amount of energy before as we do after. So 2 plus 2 is 4. And we have the total energy before equals the total energy after, showing that conservation of energy.